Okay, so I'll take slide one. So, okay, slide one is the simplest Markov chain you could come up with. It's a two-state Markov chain. Anything smaller would be too trivial. Okay. And P and Q are the probabilities of going back and forth between these two states. And when we form a matrix which has all these transition probabilities, there are four altogether, the two loops that go from one state to another, and the two transitions going from one state to another, and the two loops. If you put them in a matrix like this, that's called a one-step transition matrix. Traditionally, P and Q would be considered to be probabilities, strictly between 0 and 1. Why strict? Because otherwise it wouldn't be connected. We want this chain to be connected. It turns out the P matrix here has two eigenvalues. One of them is always 1, and the other one, it turns out to be this expression, 1 minus P minus Q. And, oh, I guess I should have said the P matrix is what's called stochastic, which means the rows add up to 1, because from any state you either, wherever you go, all the possibilities have to total 1 or 100%. Okay, now it turns out we're interested in taking powers of the P matrix. Why? Because when you take powers, that's saying that actually counts for you all the paths to go from one state to another in k steps. So P to the k is very useful. Instead of being a one-step transition matrix, it's essentially a k-step transition matrix. And this identity is called the Sylvester eigenvalue expansion. Maybe we want to put the word eigenvalue up here. And in this case, it looks like this. Eva will have more to say with that in the next slide. But what you can see from this is if this 1 minus P minus Q is between 1 and -1, this term goes away, and you get a long-term limit, which turns out to be what's in the first matrix. Eva, you want to go to 2?
Yes, and Dylan, if you recompile, I added, Dr. Koenig, I added the word Sylvester, eigenvalue.
Oh, okay, cool.
To the first one, yeah. Okay. Okay, thank you. Okay, so slide 2 is how we actually apply the Sylvester's expansion. First, it's used on square matrices with real entries, and the expansion looks like the following. M to the k equals the sum of n terms. Each one is made of two parts. The first one is the spectral projector, that's the A sub 1 through n, and the A matrix is also a square, real n by n matrix, same dimensions as M, and it's, okay, the explanation is later. Okay, so A is a matrix, it's called a spectral projector or a Frobenius covariant. It's not raised to the power, which is more convenient because we don't have to take the power of a matrix. Meanwhile, the associated eigenvalue is raised to the kth power, which is the power we're taking on the matrix M. Now, we can also use the expansion to find specific entries in M to the k, which is helpful because we're looking sometimes for certain probabilities after k steps in the chain. So that would be done by just simply using the corresponding entries in each spectral projector, the A matrices. Now the spectral projectors in the note are made by taking the outer product of the right and left eigenvectors of a certain eigenvalue, and we do that for each and every eigenvalue, with a scalar c squared such that the dot product of the pair of vectors is equal to 1. Did I miss anything, Dr. Koenig?
Yeah, maybe one slight thing.
Yeah.
The M to the K formula is very nice in this sense, and I think you said it, but I guess I'm stressing it.
Okay.
If you want to find the kth power of an M matrix, it's sort of very, what's the word? Very busy, very work intensive, because there's a lot of products that you have to do. This allows you just to take powers of numbers, which are much easier to do than taking powers of a matrix. So you can find m to the k by essentially putting the powers onto the eigenvalues. So that's sort of a nice part of it.
Yeah, I believe I said something similar, but noted.
You got it? Okay, the next slide, be rolled down, is back to the two-state one that we first talked about. And what we're doing now is generalizing. So the title of this whole talk, I can flick to the title, I don't remember it, but I know it's got to do with generalized steady state. Okay, don't flick. Either way, the title of the talk is something like generalized steady state. So we can relax the assumption that we had in the first slide that P and Q were classical probabilities, and we can replace it by this condition. If we do that, can someone roll back to slide 1? Yeah, perfect. This second term, if 1 minus P minus Q is between 1 and -1, again will disappear because the fraction is approaching 0 as a limit. And so you'll have a steady state, which is just the first row of this A1 matrix. So that's a more general condition. Go back to slide 3, please. Thank you. And so the main idea of slide 3 is replace the condition that P and Q are classical probabilities by this eigenvalue condition that it's trapped between 1 and -1. Here's an example. If you form a P matrix which has a negative transition now, the P and Q in this case, oh, this is worrisome. Why is this P and Q bigger than, oh, it's okay, I guess, because we want 1 minus P minus Q. So that would be, where's the calculation done? 1 minus P minus Q is -1/6. So it does fall in the range of between 1 and -1, which means the second term here goes away. And even though there's a negative transition in the P to the K has a steady state distribution, which is 2/11ths and 9/11ths. So what this shows is you could actually do everything we did in slide 1, even when the probabilities are not conventional. Why are the probabilities not conventional? Well, the sum of them add up to more than 1, and P is bigger than 1 itself. So even though these are sort of unusual, unconventional values for P and Q, the steady state is conventional. Yeah, and if you have anything to add, Heba, feel free.
No, I have nothing to add on that slide.
Cool, okay.
Okay, now this diagram has a lot of information to unpack, but basically the green region and the red region includes all the P and Q pairs that give a steady state distribution for the matrix in the previous slide. The entries inside the red square are the ones that give conventional steady state distribution, which means the steady state entries are positive and the P and Q values are between 0 and 1. So even the probabilities are conventional. However, there are two small green triangles that also give positive steady state distribution, but the P and Q entries are more than 1. And then the light green region is the one where we have negative probabilities and we still get steady state distribution. There are 3 lines drawn inside the steady state strip. There's the red one and the 3, well, there's 2, 3 blue ones. For each one of them, any produces this in the matrix. And the reason for that is we can algebraically show that by using the equation of the line, because it has a relation between P and Q, so they're dependent on each other. And any value that goes in for the line equation, goes in for the system, and gives the same steady state distribution. Did I miss anything, Dr. Krennic?
That's pretty good.
Okay.
The only thing that I might add is how did we get this slanted interval to begin with?
Oh, the
And
eigenvalues.
yeah, the
Yeah.
eigenvalue, if you go to the previous slide, yeah, it is 1 minus p minus q. If you set that equal to 1, you'll get one of these lines. And if you set it equal to -1, you'll get the other one. So those are the boundaries of the region. And that's why what she said is correct, that in order to have a steady state, you can go back to this slide 4 now, if you will. Those boundary lines are determined by putting the equal sign where the inequalities were on the eigenvalue condition 1 minus p minus q. So anything on the boundary won't have a steady state, but everything within here will. And then what she said was absolutely correct. These are a little darker green than over here, and that signifies that the steady state is sort of conventional. They're both positive. Things over here, the steady state, one is positive and the other one's negative, so that would be an unconventional steady state. Even though they're different signs, they still add up to 1. Down here is similar, but the reverse. So there's little meaning to this. Everything else she nailed. So sure, next slide.
What does the red signify again?
The conventional, that's when P and Q are probabilities.
They're positive and they're less than 1. So they're very, very, very standard and conventional. But the green triangles, Dylan, they have entries more than 1. And that's not a conventional probability for P and Q.
Okay.
Yeah, and the axes are the P and Q. So that's when P and Q are between 0 and 1, that would put you in the red square. Good question, though. Next slide. I forgot. Is this mine? I guess it is. Right. Yeah. So let's scroll down a little further so I can see it all. Yeah. So, this is a special case. Now, instead of looking at 2 states, we're advancing this analysis to 3 states. So if we have 3 states, 0, 1, and 2, and we wanted to keep it simple, so we're just using 2 different variables for the transitions, A and B. And this case is denoted by ABAA, which means you have well, that's not that one. This one is AABA, so it goes AABA. That goes with this. And the ABAA is describing the other one. So the difference is simply where does the B transition take place. And here it's from 1 to 0, and from here it's 1 to 2. So the P matrix is similar but different because of the locations of the A and the B. And so like we did in the 2 state, we'd like to know, is there a region for which this has a steady state? So we look at the eigenvalues of these matrices. If you scroll down, they should appear. Oh, why are these 2 put together? It turns out they have the same eigenvalues. I don't know if we're in the same case. Scroll up, let me make sure.
Yeah. So what I did, this is broken. So this is
Oh, you moved
case
over.
1 and 2, and then continued.
Got it. Okay. So, but for both of those cases, the eigenvalues are what are given here. 1 is always an eigenvalue, by the way, for all of these things. There's an easy explanation of that, which I can give you later. But all of these matrices, it's because the matrix is stochastic that 1 is always an eigenvalue. The other 2 turn out to be these, and they're the same eigenvalues for both cases. That's why they're grouped together. The steady states we are able to find are these, which look very similar to each other, except where the B occurs. In this case, 1, the B occurs on pi 2, and in this case, 2, the B occurs on pi 0. The region where there's a steady state, though, looks like this, which is interesting. Why? It's similar to what we found for the two-state guy. It's a slanted region that looks like a parallelogram. And the boundaries, again, can be found by taking these eigenvalues and setting them equal to 1 and -1. And the region in between there is what we're after. The red triangle is the classical case or the conventional case where P and Q are between 0 and 1. But the green areas over here are unconventional areas. So that means you don't have traditional probabilities, but still they have steady state distributions. The only other, well, a couple of remaining comments. One sort of thing that we haven't totally resolved. This looks like the two-state guy, but the two-state guy, the strip goes on infinitely. And this one is sort of bounded. So that's a question that we're still thinking about. Why for 3 states is this thing bounded, and for 2 states the other one wasn't? And then some of the same things that Heba talked about in the 2-state. If you took a straight line going from the origin to the boundary over here, a line segment, everything along that line segment turns out to have the same steady state as each other.
Dr. Koenig, we don't see your cursor.
Oh, sorry. So I don't know how to, you don't see it at all.
No, well, which corners or which two
Okay.
points are we drawing the line?
We're starting this, we're trying, oh, great, you'll help me. Starting at the origin and then going to the dashed line. That's not that one, the other on the other side of the, no, the one that's the diagonal dashed line. Yeah, that guy. So if you drew a segment going from the origin to that line, everything on there would have the same steady state distribution. It's not obvious, but it's sort of the argument that Heba gave before. Professor, I think that you can use the whiteboard feature on Zoom to draw over the screen. If I knew how to
You
do
can use annotate if you want to, but
well, I think I'll use Heba to help me. That worked well.
No problem.
But thank you, Constantine. Okay, I think that's it for this slide, unless I forgot anything. Heba, you can let me know.
No, nothing on mine.
Okay.
Okay, slide 6, cases. Okay, so cases 3 and 4 are the 2 chains that had the same general form of the eigenvalues, which means we got the same region for them for steady state distribution, conventional and non-conventional again. So not to repeat the same details, but we have the chains, the adjacency, the matrices corresponding to the chains, the eigenvalues, and we also found the steady state distributions, which are almost the same, but they're opposite in order. It has to do with how the chains are arranged, the one-step transitions. And then as far as the region goes, that's the shape we got. It was an intersection of a few of the graphs for the 2 eigenvalues between 1 and -1. And then the green region has the conventional steady state, so all the steady state entries are positive. The green has the ones that are negative.
Yeah, the only thing I would add to that is if you compare this case 3 and 4 to the previous case 1 and 2, you'll see the eigenvalues here are more complicated because they have a square root.
Right.
And it's that more complicated eigenvalue that gives rise to that. I think I don't know if it's a hyperbola or what it is.
It was a hyperbola, I think.
Yeah, that on the curve on the top. So we don't have the slanted interval parallelogram we had before. We have this thing with a curved boundary.
Yeah.
But other than that, everything she said is correct. And the whole title of this thing is got to do with generalized steady state. So if you stay in the red, that's the traditional Markov chain. But if you end up with values of A and B that are in the green, you still have steady states. In this case, we didn't actually say when they're both positive or when they're both negative, but I think you could see, yeah, you could probably figure that out if you wanted to. Okay, so I think the next one's back to me. And this one's even more complicated in a way than the other. Yes and no. Okay. So again, it's just a different location. This has two A's and two B's in the transitions. I think the previous cases had only one B, I believe. So, but the A's and the B's can take place in different places. Why are there the two cases in here are grouped together? Because they have the same eigenvalues. Notice one is again one of the eigenvalues, but this time the eigenvalues are not quite as complicated as the previous one, but still they got a square root in there. Now, what's interesting here is the region. Oh, well, the steady states are more complicated in this case than it was in the previous one. And again, the red is the classical region where there are probabilities. And I think what's going on here, though I'd have to, maybe I can blow that up. Yeah, red is the classical. If you can zoom in on this caption underneath it, it would probably give you the detail. The dark green is non-classical but real eigenvalues, and the light green are non-classical but actually imaginary eigenvalues. So this region is different than some of the other ones because it's sort of got this crescent shape on two sides. Anything in here that's colored will have a steady state distribution, but sometimes classical but more generally non-classical. Feel free to say any more if you want, Eva.
No, nothing to add on that one.
Okay. So keep going.
All right. Okay, next would be case 7 turned out to be unique. Oh, okay. Yeah, case 7 was unique. Right, chain, matrix, and then rest of the slide, please.
I think it's in the next column.
Yeah, so this one's broken up.
Yeah,
Yeah.
no problem. Okay. Okay, so this case had very nice eigenvalues, and the regions were also nice looking, nothing complicated. Again, the red region has the classical conventional steady state, and the green one has the non-classical, but the eigenvalues were real. Is there anything to add, Dr. Koenig? I think that's
No, it's pretty,
yeah.
This is pretty close to perhaps one of the other ones we had. I think let's go back real quick. Let's see.
I think it's similar to the first one.
Well, yeah, and I'm not sure. It's not that one. Anything that had, yeah, scroll
What do you
up.
want to look at?
We want to see, if it looks like anything else we had.
The first one sort of, because the whole thing is a parallelogram, but then inside we had a triangle for case one.
Yeah, I think it's also, I think this may be one of the cases we left off. We had this parallelogram
Right.
vertically, but I think
Yeah.
we deleted it.
Yeah, you're right. Yeah, there was one like that.
Anyway, so now she hit all the points. Go to the next one. Oh, by the way, all of these that we're showing are simple in the sense that they're only concentrating on two different parameters, A and B, and where they may occur. Yeah, so could enlarge the next slide more. There you go. So here we have a sort of an alternating pattern, A, B, or BA, BA. Notice that arrangement does give rise to more complicated eigenvalues, which give rise to a more complicated boundary. This one's interesting. Well, okay, I don't know whether that's saying. Is it saying that the steady states are uniform? Is that true? I don't remember that. Yeah,
Oh.
I guess it's saying they're all.
No, okay. I'm gonna go back to check the slide cases 8 and 9. That shouldn't. No.
Yeah, I don't remember just having 1/3, 1/3, 1/3, but
Me
maybe.
neither.
Yeah, let's check that.
Okay, yeah, I'll go back to the article
Yeah, or the article
or the talk.
or
Either
the
one.
other poster maybe, and see if it's still there.
Okay.
It's a little surprising. It's making it look, you know what? I
The
think
old
it's right.
poster, it says 1/3, 1/3, 1/3.
It's right. It's right, Heba, because you know, if you take the ratio of these things to find the steady states, B over B will be 1, and so A over A will be 1. So it's right. So this is a little surprising.
Wait.
She doesn't believe it yet. I don't think so.
No. How come I never heard of this before?
I don't know. Maybe it was one of the things that got changed as we realized it.
Okay, and I wasn't there for it. Okay.
Yeah, but if you remember how to do the steady state where you do
Yes.
the ratio of these things, well, the
Yeah.
B's will be 1 and the A's will be 1.
Right.
So it's going to give you the third. So it's right. So this one you can say is interesting because no matter what you pick A and B to be,
The same steady state.
you get the uniform steady state out of this. And then I guess the green again would be a steady state that's not classical in some sense. So that's an interesting case. What's next? This is the dual. Okay, this is tricky. So for the last couple slides here, we need to introduce a new idea. And the idea is if you have a matrix, such as the one that's inside this 3 by 3 matrix, the 0.7, 0.3, and 0, and so forth, that's a Markov chain that looks like a birth-death chain as diagrammed here. Birth-death chains just go up by 1 or down by 1 or loop. They don't have paths that go, you can't go up by 2 or more. So this is a birth-death chain, and we're trying to define what it means to be in the dual of this chain. It turns out the dual of this chain geometrically can be pictured in the following sense. You could just add one more state, which we call -1, to the existing chain, and make both the -1 and 2 absorbing states, which means once you're there, you never leave. And then all the probabilities that were going up are now going down, and all the ones that were going down are now going up. So if you create a new chain in that manner geometrically, that's called the dual. Now it could also be created algebraically. So let me show you how. If you start in the first column and you look at the first row, well, actually look at the second row, add up all those numbers, 0.3, 0.5, 0.2, they add up to 1. And then subtract the sum of the entries in the row that precedes it. It's 1 minus 1, which is 0. Whoops, try it again. Yeah, 1 minus 1. Something strange here. Oh. Okay, the problem with this, there's a problem with this. Oh, it's up here I should be working. My bad. I'm working on the wrong matrix. Pardon me. So I should go up here, 0.7, 0.3, 0.0, and 0. That adds up to 1. And then subtract. Yes, thank you, Heba. Or whoever's ever pointing it. I think it's Heba.
That's
So,
That's me.
okay, well, thank whoever was doing it. Okay. So that's how you get the 1 here. I was working on the wrong matrix. That's the P star that we're trying to form. So then going down the first column, if you add the 0.2, 0.6, 0.2 together, that'll give you 1 again, and then 1 minus the previous row will give you 0. And that's the second entry in the first row of P star. And you keep going that way until you get down to the done with the first column. So it turns out the first row of P star is going to be 1 and all zeros, and the last rows are going to be zeros and all ones. So the harder ones are the one in the middle. Let's go through that briefly. So going back to the P matrix, look at start at the second column, and look at the first row where you have the 0.3, then the 0 and 0. Add those 3 numbers together. and then subtract the 3 previous numbers that are right above it, so you'll get 0.3, and park that value as the first entry of P star. And then do the similar thing, go to the second row of the P matrix, the 0.6 and the 0.2 add up to 0.8, and subtract the sum of the previous row, which is 0.3, so that would give you 0.5, and place that in the second entry of P star. So that's the algorithm. It's described down here in the lower part of the slide. If you stare at that, you're taking the sum of one row minus the sum of the previous row. That's the j plus 1, and the j are their adjacent rows. And you're taking their difference to get the P star entries. Okay, that process is called the dual process. In this case, it turned out to be conventional. It has all its transition probabilities are fractions between 0 and 1. It doesn't always have to work that way. So at the bottom of the slide, it says P star may not exist as a stochastic matrix, but it will always exist as a somewhat stochastic matrix, which means what? The sum of the rows of P star will still be 1, but some of the entries could be negative or could be positive.
What do you want right here? I think this is supposed to be a reference.
Let's see, P star is called this. No, P star may not exist. Have the same eigenvalues. Yeah, that is a reference. So it's one of the references to the right. Let me see which one. Let me see. Well, as it is, none of them are the right one. So let me see which one would be the closest.
Which one can we pretend it is?
Yes, let's pretend it's 4. Okay, there you go. See reference 4.
I'm just gonna, what's it called?
This is hard. This is a hard slide to describe, okay? But, and I guess the one thing I didn't say is, why do we care about the dual? And it turns out that the two chains, the original and the dual, give us information about each other. So they actually, one helps explain what's going on in the other. Even though they're different in one big way, the P star one has 2 absorbing states always at the ends. And the original has no absorbing states. It's everything can go anywhere. Okay. And actually the next slide over, which I guess I can do if you want, Heba.
No, I can do it.
You want to try it?
Oh, never mind. No, I've never seen this one.
Okay. That's right. That's what I was thinking.
I'm gonna miss so much, so you go for it, Dr. Critic.
Okay. Well, actually, Dylan has seen this one in class because we just have been talking about it, and so is Constantine. So here is, this slide is sort of enlarging on how the original and the dual interact. So what we're considering here is the general 3-state Markov chain. And by the way, we could give a little ad for Sean's talk, because everything in what we've done so far, I think, has just involved A's and B's. When you go to A, B's, and C's, then the figures all become 3D, which are pretty cool. And that's what Sean is talking about in the other poster. Okay. But now this is even beyond what Sean is talking about, because this doesn't have A, B's, and C's. This says A, B, C, D, E, and F. They're no longer assumed to be birth-death. You have transitions that can go up by more than 1. So that's the most general 3-state Markov chain you could dream up. And it's got 6 parameters, A, B, C, D, E, F. And the P matrix looks like what's described below that first transition diagram. That's what that's called, by the way, a transition diagram. And if you go through the process of the dual that was just explained in the previous slide, that's the third or the second transition diagram is the dual. Notice it has absorbing states at -1 and at 2. And here's a nice relationship between them. Scroll down a little further. Oh, that's the matrix of P star. If you take that matrix P star is referring to the dual, and P is referring to the original. If you take P transpose, which is a 3x3 matrix, and transpose it, and you find the eigenvector that corresponds to the eigenvalue of 1, 1 is still an eigenvalue, it turns out that Wolfram alpha, for example, will tell you that one such eigenvalue is V1, which is written there in terms of all the 6 parameters, A, B, C, D, E, and F. And theoretically, it could be shown that you could form the steady state of the P matrix by taking the values of those eigenvectors, or that eigenvector, and essentially normalizing it so that each of the entries now become the denominator of a fraction, and the numerator is still one of those A, B, and C's. And that's giving you the steady state of the original matrix. Now, why is that useful? Well, because this is like a general formula for any 3-state Markov chain. Instead of, if you change just one of the parameters and you want to find the steady state, typically what students would have to do is just go through a system of equations and resolve them. But now this has been solved in general. So we can find the steady state of any 3-state Markov chain. And by the way, some of these steady states are classical and some of them are non-classical. And here's a cool connection. Scroll down a little further. Yeah. If you're interested in the dual, if you're starting at a state in this dual, say at 0 or at 1, and you're trying to figure out what's the probability of being absorbed at -1, it turns out to be the sum of some of those steady state distribution of the original. So now that we know what pi1 and pi2 are from above, if you go back to the dual diagram, go upstairs again. Yeah, there it is. If you were to start at 0 or at 1, the chance of being absorbed at -1 is actually found in terms of the steady state of the original Markov chain. And so that's sort of the connections that we were talking about. Last thought on this, all of this generalizes to higher dimension, to more states, but it gets pretty complicated pretty quickly to have a general formula to do it, but it still works. Okay, that's more than you're probably going to have to say to anybody, because I don't think you'll have time to do any of that. But did that help? And are there any questions?
Oh, but that helped a ton. Thank you so much.
Oh, good. Yeah, trying to explain what's going on. And by the way, if you forget part of it, you're a team there, right? So
Yeah, we fill in for each other.
yeah, so if someone forgets to say something, just like Heba and I were trying to fill in for each other as we went along, you may hit a blank or just get distracted by something, or someone may ask a question that you really just don't know the answer to. You can try, you can think about it, you should, but if it doesn't come up, you don't come up with anything, don't forget you got somebody else there. Well, if Heba's there, you'd have 3 people there. Sean will be there too. So 3 or 4 people there who actually are resource people.
If Heba shows up.
Yeah.
She's got the longest to come, so I can't say too much about that.
If my students don't leave any nerves in me, I'm exaggerating, but we'll see how much energy I have by Saturday.
Yeah, I was going to say you stick your head out the window and see if the weather is good.
Yeah, I hope there's no rain.
I could, hey, if it's pouring, I could totally understand you saying, I'm covered. I understand that.
Yeah. Oh, Dr. Koenig, today they got angry at me, the students, because I have them write expanded form for exponents, and they're like, this is tedious. And I just said, like, you have to learn the algorithm and then you can save time. And then I give them zeros because they didn't do it. It's
Oh.
what they got. That's what they get.
Yep, I'm sure you're earning your reputation there, Heba. What can I say?
I have very much earned it since last year.
The good
Wait,
thing, the good thing
if-
is you're okay. You're not, because at the start she was really, it was really hard.
Yeah, no, things are better. Yeah, you learn how to deal with, but rude behavior is rude behavior, so they're just kicked out of class, some kind of punishment. And then I tie their behavior to their grade because if they're not helping themselves or anyone, they get what they get, honestly.
So do you have a lot of behavioral problems or
Only a few eighth graders, and they're very, very good at being bad.
they're good at being bad. I love it.
Yeah.
wait,
There's
so Hiba, you have a full-time job?
Yes.
Yeah, full time. I have my teaching credential in math and English, and this year I'm teaching both math and English at a high
Wait,
school. Yeah.
So are you gonna quit that job when you join the masters?
No, I'm gonna keep it going and then take the classes in the evening
Then why do you want to be a GTA?
because it's the college experience that's adding on to my high school experience. That's why.
I don't think she wants to teach high school for the rest of her life.
No, probably not. It's good to have on the side for later, but yeah, but Dylan, I'm thinking if I do the GTA, it's better for when I apply for instructor positions instead of just having the high school experience on there.
Yeah, you get typed if you teach high school for a long time and you never teach community college, even with the masters, people could sort of say, "Oh, she's a high school teacher."
Yeah, it's because I can see how the system can like kill the creativity or just yeah, it's not always good for the teaching
But,
skills.
but what she's trying to do, I should say, on the side, is very hard. It's very hard to have a full-time job and be in a graduate program. That's a different thing.
Yeah, I mean, I had to take a 2 years break to breathe and then I can go back recharged.
Well, yeah, you learned how to control your high school class a little bit because
Yes.
it's hard. So what
Mhm.
she's doing, I don't recommend.
Well, thank you.
No
Because
offense, nothing personal, but
Yeah,
it's just hard.
it's too much. Yeah.
I'm just letting you know, I'm broke because of the GTA program. Like, it
Wait.
pays so little.
Well, yeah, that's why I have my like I this is my third year teaching, so I've been able to save money. It's a 3 year full-time job.
All right.
So I'm not gonna be broke for sure.
Because I'm talking 300 a month.
Yeah, no, it's